Welcome to Lecture 2 of Chapter 1 in Hydrology. I'm Dr. Marty Matlock. For this lecture, we're going to cover the global condition of water, where it relates to wastewater management, social, environmental, and economic benefits of achieving sustainable development. Let's take a look at the world's water resources. It's a big world. Our Earth is dominated by water, mostly ocean. The amount of marine or water on the planet is over 98% of total water volume at any given time. The demand for fresh water has been consistently increasing and will continue to do so over the decades, as we saw from last lecture, with population and prosperity demands increasing. The sectors that we use water for are fairly largely categorized as industrial, municipal, agricultural, energy production, and ecological. Urbanization, which we've discussed previously, is driving demand. 2.3 billion people will be living in cities by 2050 that currently do not live there. That growth rate is really a product of the increased population, which is predominantly urban. East Asia and the Pacific areas are seeing the most rural population growth, or decrease, annually, a 1.5% decrease annually in those regions. Sub-Saharan Africa actually is seeing some rural population growth, but the amount of urban growth is 3 times rural growth. People are moving to cities everywhere. Water scarcity, a lack of water when you need it, where you need it, is impacting 2/3 of the world's population. The impact of water scarcity is catastrophic. We can go for a little while under water rationing or some sort of water management regime, but when water is gone, cities go away. Increasing water scarcity is affecting our environment as well. It's been said that if climate is a shark, climate change is its teeth. Climate change will exacerbate the frequency and severity of floods and droughts around the planet, and already is doing so. The difficulty is knowing when and where droughts will occur and how long they will persist. Water quality is a major concern associated with water resources management. The relationship between hydrology and water quality, as we alluded to last lecture, is that the water running off the land is capturing a number of contaminants and transporting them. And the transport of contaminants results in degraded water quality in water bodies from which humans draw water for use. Among the most dangerous of contaminants are pathogens. Severe pathogen pollution affect about 1/3 of all river stretches in Latin America, Africa, and Asia, putting the health of millions of people at risk. We discussed those risks in fairly extreme terms in the last lecture. Take a look at the red lines on this map. These are the areas where we have severe pollution in Latin America, Africa, and Asia in particular. The green lines represent areas where we have relatively low pollution. Now, the gray areas that have not been computed are relatively developed economies. They still have problems. We certainly have polluted water in the United States. For example, in Oklahoma, the entire system of rivers and lakes have fecal coliform counts greater than 200, which puts them in the yellow zone at some time of the year, which makes them not appropriate for primary contact recreation. That is to say, the state of Oklahoma has declared you should not swim in their waters because of fecal coliform contamination. Because we are urbanizing, we are capturing more water to use in our municipal, industrial, energy generation, and manufacturing and other sector activities. That water is then collected in many systems and discharged into another water body generally, and oftentimes not treated. The quantity of wastewater produced and its overall pollution are increasing as urbanization and human populations increase and as we become more prosperous. As the overall demand for water grows, the quality and quantity of wastewater is changing. Wastewater quantity is increasing and quality is decreasing overall. Agricultural water consumption accounts for about 38% of the water that we draw from the environment. Consumption means it's collected, applied to the land, and evapotranspired, so it can't be used. About 32% of the water we extract turns into agricultural drainage. That means that about 70% of all the water that we use on the planet is for agriculture. 16% is industrial wastewater, 3% is industrial water consumption. Consumption means it goes out in a bottle of Coca-Cola or is evaporated. Municipal water is 8%. Municipal water consumption, the water you and I drink, is 3%. 80% of the world's wastewater is released into the environment without treatment. It's more wastewater than ever. 80%. The impact on human health and sanitation is substantial. Sustainable Development Agenda focuses on this, as we discussed in the previous lecture. Access to improved sanitation is one of the most important measures we can take as a species to improve overall human well-being. 2.4 people do not have billion people do not have access to improved sanitation. Nearly 1 billion people worldwide still practice open defecation. That means generally in the streets, where people walk, where children play, where animals eat. Remember our population growth map. Take a look at our areas without sufficient sanitation, less than 50% or 50 to 75% sanitation, access to sanitation. Amazingly, much of Russia does not have access to open sanitation or to public sanitation. Now, they generally don't practice open defecation, but they use outhouses and other primitive means of sanitation. You're familiar now with the 17 Sustainable Development Goals. Goal 6, Clean Water and Sanitation, has a number of sub-goals. Goal 6, Target 6.3, by 2030, improve water quality by reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals and materials, having the proportion of untreated wastewater and substantially increasing recycling and safe reuse globally. You can imagine how achieving this target, SDG target 6.3, would improve our ability to achieve many of the other targets. That is, good health and well-being, reducing hunger, decent health, work and economic growth, as well as sustainable cities and communities, life below water and life on land. All would be improved if we achieve this goal. It's all about water quality. 71% of the world's population will use safe, managed drinking water services by 2030. 45% of the world's population will use a safely managed sanitation service. 60% of the world's population will have access to basic hand washing facilities. At the global level, not enough country data were reported in 2015 to figure out what we're doing with wastewater. So we still don't know. The same with water quality and water use efficiency. We want to reduce our water scarce areas, increase water management. We want to decrease transboundary conflicts, increase ecosystem processes, and increase the amount of money we work on cooperation and participation. These are all part of the global improvements we seek. If we look at drinking water availability, unfortunately, gray is the dominant color. These are areas we just don't know about. These are unknown unknowns, commonly referred to as unks. When you just don't know, it's hard to manage. We do know we have the areas of orange and yellow where we have greater than 50% of the population does not have access to safe drinking water. 80% of the world's wastewater is released without treatment. These are the regions where that occurs. I'd like to point out it's not all just developing economies. Look at Europe. Developed economies, Ireland, Portugal, also struggle with these issues. And Australia, for that matter, New Zealand. Global water quality is addressable in a very positive way. Treating water is a technologically sophisticated and valuable process. That is to say, it creates more value than it costs. And it also creates good jobs. The water that's discharged after you treat it has high value in areas and then goes back to the ecosystem where it can be utilized downstream without additional cost. Discharging untreated waste means somebody downstream is impacted by it. They bear the cost either directly through impacted health or indirectly because they have to treat the water in order to use it first. Wastewater treatment and hydrology are intimately connected because, as you can see in the background of this picture of a wastewater treatment plant, the water coming off of that city into this wastewater treatment plant is not just through pipes. It's also running off of these lands, these urban systems, as stormwater. In many cases, they're still co-collected. That is, the sewers collect the stormwater and they're commingled and have to be collectively treated. Water quality concerns around the world are not diminishing. If you look at waterborne disease instances and water-carried disease instances around the world, you can see that they're globally distributed. Europe is our biggest hotspot. That's partially because that's where we have the most data. We know that if we had more data, we would probably see more dense hotspots, certainly in areas around highly populated countries like China and like India. Note Japan on the map with its dense concentration of impacted water quality, waterborne diseases. 1.8 billion people today use a source of drinking water contaminated with feces, putting them at risk of contracting cholera, dysentery, typhoid, and polio. You can see the rate of increase in reported outbreaks of infectious disease over the last 30 years, and that rate has only continued to grow in the last 10 years. We'll talk later in the semester or the class about water quality criteria, and we'll talk explicitly about what contaminants, what the classes and categories of contaminants are. But in general, if you have fecal coliform counts, which are the best indicator of human pathogen contamination in water that we have, if you have them 200 coliform forming units per 100 mil or less, then we consider that low pollution. 200 to 1,000 CFUs, coliform forming units. That's what CFU means. That is the number of little, if you put 100 mils of water through a filter and then put that filter on a medium and let it grow for 24 hours, you can see the little specks of coliform bacteria on this gridded system. And if you can count more than 200, you've got moderate pollution. If you can count more than 1,000, and you only do that by diluting, because you can't really count 1,000, that's just one big smear of colonies on a plate. But you could count, if you dilute it by 1,000 and you count 1, that's 1,000. If you can't dilute by 1,000 and count 50, well, that's 50,000. So that sort of pollution would be severe. Generally, we say that if you have less than 200 CFUs per 100 mils, that's suitable for swimming, bathing, fishing. 200 to 1,000 is only suitable for contact during irrigation and fishing activities, but not swimming. Certainly not drinking. Over 1,000, it's generally unsuited for any human purpose. The areas we see in yellow and red have over 200, and in some cases over 1,000, more than 1 month a year. We should not have this problem in 2020. So if we remember that 200 is the cutoff, if we look at this, at these box whisker plots from Latin America, Africa, and Asian streams, this is a log scale on the left, which means 200 is just a little bit above the 100, about where the average line is for Latin America. It's about 200. So the average streams, 50% of the streams in Latin America, based upon this box whisker plot, are moderately or severely polluted. These things go up to over 10 million. In Africa, over half the streams are severely polluted. And in fact, 75% of this, more than 80% of the streams are polluted, moderately polluted. In Asia, it's about the same as Latin America. So you can look at the probability distribution functions and you sort of see them. Africa's staggered because of really less data. The more smooth the lines, generally the more data. So if we look at where our global water quality concerns are, with pollution threats being in red and low yellow, now let's take a look at the whole world. We see the U.S. has a lot of yellow and red associated really with the Mississippi River drainage system and coastal drainage areas. And that's largely from agricultural and industrial discharge, with some big municipal discharges around Atlanta, for example. Look at Europe. Europe is predominantly, and Germany in particular, yellow and red. So the reason and in China and Africa, the reason we see that much of the blue in, of course, the Arctic, subarctic, as well as the tropics in Amazonia and to a lesser extent the Congo and northern Australia is because they have low population densities there. That population density is everything. Remember, a majority of the world's population lives in urban areas now. If we look at these populations in 1,000 millions, which would be billions, so 1 billion, 2 billion, 3 billion, we can see that as of 2015, we had more people living in urban areas by far. Actually, we became an urban species about 2008, where more than half of us lived in urban areas. Rural populations are stable to declining. Our populations are increasing dramatically in urban areas. We will have over 6 billion people in urban areas in the next 30 years. The need for managing wastewater, managing runoff for hydrologists is going to only increase dramatically at the rate of this curve. Urban centers impact hydrological systems in 5 very specific ways. These are necessary to remember. Increase runoff for storm events because you're paving over surfaces, which we will discuss as we talk about watershed hydrology. Increase pollution carried off in that runoff. increased water diverted from municipal, commercial, and industrial uses. So that increasing diversion of water from rivers, streams, and lakes and groundwater into urban systems means that water is now collected in pipes, tanks, and being pumped around the cities and industries, and then ultimately discharged. So that means increased channelizing for flood and increased discharge of wastewater into rivers, streams, and oceans. So our 2030 agenda, that's for the next 10 years, is to improve water quality by reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals and materials, having the proportion of untreated wastewater substantially increasing, recycling, and safer use. You can see indicators across, these are our metrics for wastewater indicator, low-income countries, lower middle, these are categories, lower middle income, upper middle income, and high income countries. We want to move from baseline, we want to have that. So 30% of wastewater treatment to 15% discharged without treatment, 62 discharged without treatment to 31 in middle incomes, 92 without treatment to 46 in low income. So how do we meet these challenges? Well, we need to manage our water better. Here we have an aeration basin. You see all the bubbles of with the bacteria and the wastewater, and a clarifier. It's a cone-shaped, usually about 40-foot deep cone, and water settles, and you have a skimmer across the top that takes all the floaters off. Reducing, removing, reusing, recovering. The 4 R's of wastewater, of water management. Reduce the amount we use and therefore wastewater we generate. Removing the wastewater into a wastewater treatment plant. Reusing it where we can, recovering what we can. Wastewater is not a burden, but a valuable resource. This is the same with stormwater. Reducing or preventing pollution at the source is the key, whether it's in a pipe or on the landscape. Pollution prevention and the minimization of wastewater flows should be given priority over traditional after-use treatment. It's the ounce of cure is worth a pound of, or ounce of prevention is worth a pound of cure adage. Removing contaminants from wastewater collection and treatment requires a process of collection using natural system treatment, which we can design as hydrologists, usually wetlands, as well as physical, biological, and chemical treatments. In Brazil, the cost of simplified sewage, it's low-cost sewage, per person has been shown to be twice lower than the cost of conventional sewage, $170 versus $390 per person. A simplified sewage is really using wetlands. The thing about wetlands is there's nothing free in this world. What we do with physical, biological, and chemical treatment is we amplify what happens in natural systems. We speed it up. We make it more compressed so that you have less land area. Natural treatment systems can do just as good a job, but they take more time and therefore more area. Healthy ecosystems can complement engineered solutions for wastewater treatment in very cost-effective manners if you have the land and the time. Time meaning hydrologic retention time. And we will design these from headwaters all the way to outlets, moving through these baffled vegetation systems, very effective at water treatment, but also slow and prone to flooding from rainfall. Treated water can be used for a number of purposes. Irrigation is the most obvious because of the nitrogen, phosphorus, and other things. But you have to be careful because industrial wastewater can have heavy metals that persist and other toxicants that are dangerous and can concentrate in plants. Aquifer recharge, industrial processes like cooling water, heating and cooling in other processes. The fact is, wastewater coming out of municipal systems is fairly constant in temperature, and so it provides a thermal mass that can be used for heating and cooling buildings even in wastewater treatment plants. And finally, properly treated potable water for full recycling. Wastewater has organic carbon in it, which can be biodegraded to methane for fuel, nitrogen, phosphorus, and potassium, which are incredible fertilizers. Recovering of these can reduce the cost of otherwise recycling complex wastewater. These investments, though, require administrative foresight, and management. Those two things are very lacking in most public works systems. So creating and enabling an environment for change. How do we change the way we think about this thing called water? First of all, we need suitable legal and regulatory frameworks. 11 out of 22 Arab states have adopted legislation permitting the use of treated wastewater. We need cost recovery and appropriate financing mechanism. The cost of improved wastewater management are usually outweighed by the benefits in terms of human health, socioeconomic development, and environmental sustainability, but no one pays for those three things directly, only society indirectly. So how do we get people to pay for the benefits, or pay the costs that we all benefit from them? Minimizing risk to people and the environment. Exposure of vulnerable groups, especially women and children, to partially treated or untreated wastewater requires very specific attention. This is a racial, ethnic equity issue. Building capacity and knowledge. Capacity building research and development aimed at improving wastewater management generates employment opportunities and promotes growth. This is a filamentous algal bloom that you're seeing here. See that it's sort of bubbling to the surface. It's because in the daytime it's producing oxygen under these algal mats, and those oxygen bubbles actually bring these algal mats to the surface where they get more access to CO2 in the atmosphere and can grow even faster, and more access to sunlight. So it's a sort of an adaptive colony approach for managing its life cycle. The nighttime, it's photosynthesizing less, there's less oxygen, and it floats back down to the bottom where it consumes nitrogen and phosphorus. Daytime, oxygen generates, it floats to the top. This diel migration of algae is incredibly complex, but it's one of the difficulties in managing it. This is probably Spirogyra, which is a filamentous algae that tends to have long cotton-like branched filaments, which makes it stick together like this. The problem with this is that is all of this biomass is carbon, nitrogen, phosphorus, is living carbon. And so when it dies, first it's consuming oxygen at night, all night long, and that oxygen is competing for, or it's taking up, is not available for fish and other things. So it creates nighttime oxygen suppressions. These shifts in oxygen, dramatic shifts in oxygen and other water and carbonates shifts the pH dramatically over the period of 24 hours, creating a very hostile environment for aquatic life. Raising public acceptance and social awareness is the key. If people don't care, they don't do anything. People have to care to change things. How do you make people care? People need to understand. Water reuse schemes, water treatment schemes, water management schemes mean that we have to be able to teach people so they understand. Raising public acceptance and social awareness is critical. You can see an astronaut with his glob of water in zero gravity. The key here is to move us, and that, of course, astronauts reuse their water to a certain extent in the International Space Station, and certainly will as we colonize Mars and the Moon. Extensive information campaigns and participation by the public so that we understand our water treatment system and have confidence in institutions for treatment is going to be critical so that we can recycle water effectively. So here are take-home messages. Wastewater is increasing worldwide, vast majority without treatment. Low-cost treatment options are available. Reliable and sustainable sources of water are critical. Sustainable sources of energy, nutrients, and other recoverable byproducts can be collected. Circular economies, wastewater use and byproduct recovery can generate new business opportunities. Costs of improved wastewater management are way outweighed by benefits in terms of human health, socioeconomic development, environmental sustainability. These are essential for achieving our goals for the 2030 agenda in the next 10 years. Thank you. This concludes Lecture 2 in our Introduction to Human Impacts of Water.